Okay, so there were some questions in class about showing if a system is linear and time invariant. So I'm going to look at, this is 2.1G from the book, the textbook, and in this particular case we have a system, and with input x of t, the output is an integral of that signal over 2 seconds. So if we have, just to visualize some signal, the output at any given time is going to be equal to the integral from 1 second, so we'll call this big T, I guess, t minus 1 up to t plus 1. And so the output at any given time, capital T, is the area of that integral. So we need to check first to see if we have a linear system. And so we know we need to do two things. Look at scaling. So first we'll look at that. In this case, if we have C, which is a constant times the input, we should have that same constant times the output. So let's put C times x of t into our signal, or into our system. So we'll just pop it in there. That's d tau. And that's a constant, so we can pull it out of the integral. And that, of course, now is just c times y of t. So it shows that the scaling property works. So check. We have to look at additivity. And in that case, we'll put two inputs in at the same time. And the output should just be the output from x1 of t plus the output of x2 of t. So very similar now. We'll take our system and we'll pop in our new signal, which is really the sum of two other signals. These are taus. I keep forgetting to put my little dummy variable in there. And we have this property of integrals. We can integrate each piece separately, right? And that is going to be equal to y1 of t plus y2 of t. So we've shown that its additivity property works, scaling property works, so yes, it's linear. So now the one that always seems to be a little trickier is time invariance. So let's first we're going to delay the input by some constant t, and so now we're going to get an output from doing that. Right? And so now we're putting into our system this delayed input, and we get something like that. If we look at the output, if we look at y of t, y of t is equal to this, so we come through and we essentially replace all the t, little t's, with t minus our delay. So now we have t minus 1 minus t, t plus 1 minus t, right? Just replacing the t with t minus t, x of tau, d tau. So it's just changing the limits of integration because that's where the t is appearing. And so we have the same signal, but the area over which we're finding that integral has moved, right, by that delay. Now the question is, are these two things equal, right? Because if they're equal, it's time invariant. And to do that, what we want to actually do is do a change of variables. So we'll do that over here. We'll say tau minus big T, we'll just give it a new name, tau prime. So tau is equal to tau prime plus the shift. D tau is going to just be equal to d tau prime. We can say if tau is equal to t plus 1, then tau prime, right? Because that's the limits of our integral. So when tau is equal to t plus 1, tau prime is going to be equal to t plus 1 minus the delay. And similarly then, when tau is equal to t minus 1, tau prime is going to be equal to t plus 1 minus t. So we can make all these substitutions, right? So up here we can have now t plus 1 minus the delay, t minus 1 minus the delay. Again, substituting in these values of tau, right? You maybe have done this before in class where these are constants. In this case, they're variables, but it's still, we're evaluating tau at t plus 1. After the change of variables, we're evaluating tau at t plus 1 minus t. And then we have tau prime, d tau prime. And this is just a dummy variable, right? So it's fine, and we've actually shown now that these two things are equal. So yes, it's time invariant. But the trick was to do this change of variables.